My name is Amelia Dodson, and this is my Lab 5 on the falling slinky. So the purpose of this lab was to model the motion of a stretched slinky dropped from static equilibrium as shown in a previously filmed video. The models and fundamental principles used were forces, Newton's second law, and gravity. A major assumption that we had was that the person holding the slinky does not move, and that the system was a spring and the surroundings was the earth and everything else. So as a preview, the bottom of the slinky stayed stationary, and in order to complete this lab, we used Tracker to analyze the motion, and then we also use GlowScript to create computational model. So going into the fundamental principles, first of all, we have drag force, which is resistance force caused by the motion of a body through a fluid like air. In our case, it was the slinky moving through air. And then Newton's second law, which states the force acting on an object is the product of the mass and acceleration, and from that we can get the momentum formulas as well as the position and velocity update formulas. Lastly, we have universal gravitation, which states that gravity is the force of attractions between any two objects with mass. So some important values that we had was that the mass of the slinky was 0.218 kilograms, the height of the person, or the height at which it was dropped, was 1.75 meters. The initial position is what is shown on the slide, and then the initial velocity was 0. So going into our computational model, which was done through GlowScript, we are starting off with our initial conditions, which just inputs a lot of the values that were shown on the previous slide. And then we had 2 while loops. The first was understanding the motion of the bottom of the slinky. In this section, it's really important to note that the net force is 0, whereas the other while loop, which is analyzing the motion of the slinky as it's falling, the net force is no longer 0, as there is the addition of the drag force as well as the force of gravity. So going into our results, we can see that the computational model aligns very closely with the observed motion of the slinky, but there are some slight deviations, but these could be for a couple reasons, including there are external forces that are not accounted for. One of those big things could be wind, as well as inaccurate tracking on Tracker itself, which is just human error due to slight deviations when plotting the points. But it's really important to note this top section that's completely straight, which is indicating that the bottom of the slinky is not moving. That's it. Thank you so much.